To get height curves for a site in Stockholm municipality, as well as in a neat way get an estimate of a reasonable excerpt or crop of a map for a certain scale, it is recommended to use dpFieldmap. Navigate with the mouse to the area of interest. Maneuver with the left mouse button as long as Pan is the selected tool. Zoom in and out with the scroll wheel. In the Map tab, one can change what set of layers is shown by changing between the presets. Examples given are the real estate map, which is best shown a little more zoomed in, autophoto, city map, etc. In each layer set, any sublayer can be toggled as visible or hidden. A black text signifies that the layer is shown scale dependent, depending on the scale shown down here in the lower left corner, while a blue texted layer will always be shown, and the grey layer will always be hidden. If you want to hide a specific layer without knowing where to find it in the Layers pane, you may click Show Attributes. This changes the active cursor tool setting to the Show Attributes tool. By clicking an object, you get some information about it. Generally, the actual information given is totally lacking, but clicking any object now will enlighten you as to which layer the object you want to hide is part of, as in this example, gatuhöjd THB. Using this text string to filter out the layers, you can easily find the culprits and hide it or its parent layer entirely. To pan while any other cursor tool than panning is active, as in this example the Show Attributes tool, simply hold down the middle mouse button, otherwise known as a scroll wheel click. Let's change back to the pan tool. Since you cannot, as of our understanding, save any custom layer states, it is advised to find the one preset which mostly aligns with your intentions, and optionally write down or take a screenshot of the customizations you prefer, since any custom manipulations made will be lost should the program crash before successful export. For a 2D output, the default height curve layer is adequate, but it consists of segments broken by the building footprints. So if you intend to use the map for 3D, it is important to instead show the layer group height curve UUH without breaks. Even though one might assume that only the even and odd sublayers are sufficient for a meter per meter height field, the 5 and 10 meters curves must be active as well, since they are excluded from and complementing the even and odd height curves layer. The 0.5 meter curves are generally absent from the data, even though the layer exists. To reset any sublayer to its default setting, simply right mouse button click it and click Reset. To reset a whole layer set, simply choose the map again in the list pane. When you are satisfied with the map you have in front of you, you may export it. While it is entirely possible to export it immediately via Archive, Export, DXF, this has the drawback that you have to trust your intuition as to how far to extend the excerpt or crop that you make with an arbitrary rectangle. A much better way, in terms of estimating a reasonable crop, is to first use a feature called free plotting. Under Archive, Free Plotting. The printer setting can actually be left as default, since we will not actually be exporting from the free plotting interface, but if one would want to do that, please change the printer to the Adobe PDF printer, if installed. The format, however, must be changed to conform with what you intend to make out of the map. If your deliverables requirements state that you shall deliver a situation plan drawing in a scale of 1 to 1000 printed on A3, then change the paper to A3. If you want to do a large site plan drawing in a scale of 1 to 400 printed on A1, then change to A1. The margin values will affect the final dimensions of the export, so if you want a full dimension output without margins, change the margins values to 0. Then you can change in the printing options so that the crop is dependent upon a certain scale, corresponding with your intentions and deliverables requirements. In this way, one has a perfect preview of just how much data one needs to fully cover the intended formats in the intended scale. Please note that the rectangle size is not automatically updated when changing the paper format, but one has to first switch between any other crop setting and then back to the scale one for the format change to be effective. When you have decided on a suitable crop, click to confirm the position of the rectangle. A red 1 will be showing in the center of the confirmed crop. Click Preview in the left-hand pane to continue. Now you see a preview of what an actual print of the crop map might look like. If your mapping endeavors are no more than what you see here, perhaps as something to sketch on, you may save it as a PDF by clicking the Save as PDF button. Choose the Save alternative, confirm with OK, specify a file directory, and press Save to save. But in most cases, you want to further refine the map in a software such as Rhinoceros, AutoCAD, or Illustrator. While you could use Archive, Export, DXF here in the preview window, this would only export just the geometry contained precisely by the previewed crop. And should you in future refining want to slightly move the center of the map, then that would mean that blank areas might appear in the print. Therefore it is suggested to export with a little extra margin. Do not close the preview window, this would eliminate the already placed rectangle, but minimize it in order to return focus to the main window. In the main window, go to Archive, Export, DXF. Change Area to Rectangle. It is recommended to use an exported line width of 0 if you are going to further refine the map in Rhinoceros or AutoCAD, but if you are going straight to Illustrator, then feel free to use the reference scale option. For height curves to be properly placed in the z-axis, it is important to make sure that the dimension output is set to 3D. As for the coordinate system, dpFieldmap uses a native coordinate system of SweRef 991800 for x and y, and RH2000 for z height. All Cartesian coordinate systems deal with the problem of projecting two-dimensional axes, as in the x and y coordinates of a two-dimensional map, on an object, Earth, which is inherently three-dimensional and not even a perfect sphere, but an irregular ellipsoid. The SweRef 991800 is a regional coordinate system for the Stockholm area, and differs significantly from the nationally standardized SweRef 99TM, in such a way that it is more accurately oriented in relation to Earth's true north, but this is only true along the 18 degrees eastern longitude, and the farther from Stockholm you get, the less accurate it is. The national standard SweRef 99TM uses a neat scaling trick of the reference ellipsoid to achieve an adequately reliable coordinate system for the whole of Sweden, but the regional coordinate systems are still more accurate for their respective areas. Depending on your assignment, you might want to work in a certain coordinate system, but in most cases either one will do, as long as you are consistent and do not mix data from different coordinate systems. All data from dpFieldmap are natively in SweRef 991800, but all vector data can, during DXF export, be converted into SweRef 99TM, among others. The raster data, as in the autophotos, cannot be converted, but in an image manipulation program, such as Photoshop, they can be rotated and skewed to conform to the SweRef 99 coordinate system, preferably by using a reference map made from converted vectors with the correct coordinate system as a separate layer. All geographical data from SLU, obtained from the geodata extraction tool, is delivered in the SweRef 99TM coordinate system, so it might be advantageous, simply for the ease of combining data, to use the national coordinate system, unless otherwise is explicitly necessary. Thus we will change to SweRef 99TM in the export settings. Choose a file name and a directory and click Save. This will initiate the drawing of a rectangle for the data crop. Add a margin of 15–20% on each side by clicking adequately outside of the lower left corner of the previewed crop, and then do the same outside of the top right corner. This will export a crop according to the settings you define. Navigate to where you saved your exported file, click and drag the file into the Rhino window and release it. Choose to open the file. This is equal to clicking File and Open and navigating to the same file. The import settings can be left at default, but one has to make sure as to select meters for the model unit, since dpFieldmap delivers the model in meters. Here we have the exported file. To improve upon the future overview of the layers, it is recommended to create a new layer named dpFieldmap or otherwise, to move it to the top of the layer stack, to select all other layers, perhaps except the empty 0 layer, and then to click and drag them to make the dpFieldmap layer the parent of them all. Thus you can easily toggle the visibility of all layers as long as your current active layer is not a sublayer of it. So I'll change the active layer to 0 by checkmarking here or double clicking. And then we can toggle the visibility of everything exported. I'll double click on the perspective name tag here so as to maximize the viewport, still having all the other viewports easily accessible here. And I can as well double click again to get to the 4-view mode. But now let's resume to the perspective viewport, maximized. One can see here, holding down right mouse button and moving the mouse will rotate the camera. And one can see here that while many buildings have their footprints floating in space to be assumed at their correct Z height in the XYZ coordinate system, some of the buildings lack this information and are positioned at Z0. By holding Shift and right mouse button, you can pan the view. Some bewildering examples are to be expected as well. By clicking on an object, it will select it, and typing ZS as a command will zoom to selected objects. Press space or enter to confirm, hold right mouse button to rotate and orbit the camera, and you can see here that this is a bewildering example. But this is of no concern as of now, since we will be focusing on the height curves. Typing ZEA will zoom to extents of all objects. Confirm with space or enter. The luminous green height curves are ordered in the same layers as was defined in dpFieldmap. Here. If one looks closely, one can see that this is character coded. G is for geometry, L is for line, H is for height data, and we got text layers as well, and these are categorized as text of height. The text layers, if one right-click on a layer and select objects, it will select all objects pertaining to that layer, and one can then, with those selected, type ZS, zoom selected, press space or enter to confirm, and it actually didn't do anything because, or not much at least, because of the distribution of these objects. They are everywhere, but one can zoom in either by scrolling in and out or by holding Control and right mouse button, and that will be a more precise scrolling. And one can see here that this was the even meter height curves text layer. To make for easy toggling and selecting, we can create a new layer here. Let's select the first one of the height curves, click new layer, assign a name of height curves, click this button to move it up 1, so that it is on top. Click on the first height curve layer and hold shift and click the last, and all of these layers will be selected and readily to be clicked and dragged to be assigned to height curves as height curves parent layer. And while we're at it, we might as well create a new sublayer to it called text. One can also do this by clicking on the intended parent and clicking on this icon here, new sublayer. It will create a new sublayer. We can assign the name text, press enter, and then we can find these text layers. So everything with a T here in the suffix. To select several layers which are not necessarily consecutive, you can hold Control and click, which will toggle their selection. So there we have all those text layers. We can drag them into the text sublayer, which then will make these sublayers of the parent, which in itself is a sublayer to the parent height curves. In this way, we can both easily toggle the height curves data all together and also showing the height curves without showing the text. We can leave the text layer hidden. Zooming out and perhaps double-clicking on the perspective here so as to get the full view, we can go to the top viewport by double-clicking on its name. Having made some refinements to the layer structure, we can actually save this document, give it an appropriate name, and save it in an appropriate directory. And having done that, we can see here that the conversion in coordinate space from the regional SWIREF 99 1800 to the national SWIREF 99 TM has been made, since the preview rectangle that we set in dpFieldmap has been a little rotated, as well as the whole crop. The difference in orientation between the two coordinate systems is about 2.58 degrees, and as previously stated, the regional one is a little more accurate in the vicinity of Stockholm, but more and more inaccurate the farther away you are, while the national one is adequately accurate for all of Sweden. Both of the two are entirely valid to use as long as you are consistent in your choice, and the Earth's true north will not change depending on your choice. But the different coordinate systems will have slightly different representations of it. Nevertheless, both are theoretically correct according to their own explicit projection method of the ellipsoid Earth into a horizontal Cartesian XYZ coordinate space. One can see here in this image how the national SWIREF 99 TM coordinate system treats all of Sweden as a single map entity, with north pointing up in the whole country, even though the true north is actually straight up only along the 15-degree longitudinal meridian. The Stockholm 1800 coordinate system is oriented more accurately to the true north, but this is only completely true straight along the 1800-degree longitudinal meridian, and applying it to another part of the country may yield a larger error than the national one. Since the preview rectangle was made in dpFieldmap in its native SWIREF 99 1800 coordinate system, it has been rotated along with everything else during the conversion. But since we generally print out papers either in portrait or landscape mode, but rarely with a 2.58 degree rotation, we'll rotate the rectangle so that it is orthogonal while still keeping it centered. Clicking on the rectangle and going to Object Properties. If this is not showing here, it might be because it is situated along these tabs. It can be easily dragged out in the viewport and then positioned as a lower pane here. We can see in the Object Properties that the rectangle is in the layer lasso, lasso, lasso 0. So we'll go here to lasso, lasso, lasso 0 and right mouse button click it and choose Duplicate Layer and Objects. This will duplicate the layer as well as any objects pertaining to it. Assign the name A3121000. Press Enter to confirm. Move the newly duplicated layer out of the dpFieldmap layer hierarchy. If accidentally parented to another layer, as here to the 0 layer, one can click this button, move up one parent, to remove that parent. Make it equal. Now we can toggle the visibility of the imported data, the dpFieldmap parent layer here, and select the duplicated rectangle. Type rotate. Press space or enter to confirm. Make sure that OSnap is active here in the lower pane, and make sure that center is checked here as an OSnap option. Then hover along the interior side of the rectangle polyline and click when center is showing. Make sure that perpendicular is checked as well here in the OSnap option, and find the geometrically perpendicular point, perp, on any of the rectangle's 4 edges and click. Then make sure that orthogonal is active as an orthogonal snapping, and click when you have rotated the rectangle so that it is orthogonally to your view. Now you have rotated the rectangle. The rectangle is in the size of an A3, scaled to 1000 of its dimensions, so a print in a scale of 1 to 1000 will fit precisely one A3. We can demonstrate this by using the distance command. Type distance, press space or enter to confirm. Click one corner and then the other, and then we can see that it is approximately 420 meters. One can also see that it is not exactly 420 meters, but that is not an error in scale. The exported data from dpFieldmap is exactly 1:1 in real-world scale. But instead it is because of the margin of the export. This preview rectangle is defined by the margins of the printer settings chosen in dpFieldmap, and as you might remember, we chose 0 margin, but the Adobe PDF printer that printed it had a minimum margin of 0.13 millimeters, I would guess. But this is not a problem in a practical scenario when actually printing. You will be more limited by the forced margins of the printer where it leaves a blank space, because it will not fill the whole paper with ink. Showing the dpFieldmap layer parent again, we can hide the imported lasso layer, since we have an orthogonally rotated rectangle. We will now show 2 different methods of generating surface geometries from the imported height curves, each with different complexity and results. We'll create a new layer called Landscape. We will then make a new sublayer by clicking on the New Sublayer button here when Landscape is selected, and we'll call this Patch from Curves. We'll make sure that this layer is active. The active layer is the layer that every newly created objects will get automatically assigned to. So that is the logic behind, with care, choosing your active layer. One can mark a layer as active either by clicking in this small column here or by double-clicking. Having made sure that the text layer is properly hidden and thus unalignable for object selection, we can right-click on the height curves layer and choose Select Sublayer Objects. This will select all sublayers, all layer objects and all sublayer objects who have this layer as a parent. And now, with all these height curves selected, we can type the command patch. So P-A-T-C-H. Enter or space to confirm. Showcasing a 3D object in a planar top view space is not the most pedagogical, so we'll double click top layer so as to get to the 4-view mode, and then we can double click perspective again, and now we are in perspective mode. And now we can rotate by holding right mouse button and moving the mouse, and when it comes to patch surfaces, the main option here is the surface U spans and the surface V spans. They control the density of surface-defining curves in the generated surface object's own X and Y directions. This will be more evident when we test this out. Patching curves is straightforward, but takes some time to process, so start with small values, preview, and go upwards in density until you are satisfied. Right now, the perspective viewport that we are viewing here is in wireframe mode. This will render curves, text, and hatches on screen, and the edges and surface defining curves on 3D objects, but not any actual surfaces or meshes as 3D objects. To change the display mode of the viewport, simply click the small arrow by its name and change to shaded. This will show 3D objects, such as a surface patch. Then I think we should have actually previewed it, so we can preview it here. If we change back to wireframe mode, you see that you still see the control curves or the surface defining curves here, the ISO curves, but it's only when we change to shaded or another of the shaded viewport modes, viewing modes, display modes that is actually shown. 5 is a very, very low value, and the results will be very inaccurate, so we can try with 10. And click preview. This is better, but still yields immersion breaking oddities, like this hole here. Let's try 20 and preview. 20 is not perfect and the hole has turned into a bulge, and this is because the patch command, it interpolates these curves here, and it notices that these two small curves are 1 meter higher than this large curve and this large curve, as well as, and this curve is 1 meter above as well, and thus it tries to make a curvature which matches the existing lines here, the existing curves. And depending on the density, the interpolations are more or less accurate, but can still yield unexpected results. Okay, even with 30 as density, we cannot get rid of this oddity. It's right underneath the pool here, but the elevation itself should be approximately leveled. So we'll try 60. Alright, 60 might have done it, but it took an awful lot of time. Let us proceed with it anyway, for demonstrative purposes. Click OK to accept the preview. Holding Shift and right mouse button to pan. You can evaluate the results. And holding right mouse button to orbit, you can further evaluate. I'd say that it's not perfect, especially here around Sveavägen as well, but it looks approximately correct. Click the generated surface and either type in split and press space or enter to confirm, or simply hold Ctrl, Shift and S for the keyboard shortcut. With the split command active, you are requested to select cutting objects, and we want to use our A3 rectangle as the cutting object. And while we actually could select it here in this maze of curves and lines and ISO curves and control curves, we can just right mouse button click the layer that we know that it's assigned to and select objects. And thus we have selected it properly. Press space or enter to confirm, and our newly generated patch surface has been split by the A3 rectangle. By holding down Ctrl and clicking the interior part of the split, the one we want to keep, we deselect the interior, and with the exterior still selected, we can press delete to delete it. Alright, now we have the landscape surface model here, and we can hide the dpFieldmap parent layer so as to get a glance on it in itself. And as of now, it is a paper thin surface model, but we can give it some solidity by extruding it and then making sure it has a flat bottom. We do this by selecting this surface, and then we type in the command extrude surface with SRF as an abbreviation. And we press space or enter to confirm, and then we extrude it far beyond the bottom, or far below the Z0 plane. Click to confirm. This will make it, if we select it, a closed solid polysurface. But it looks, as you see, it has the same bottom as the top, and this is not according to expectations when it comes to landscape models. So instead, of leaving it like this, we create a plane by typing plane as a command, press space or enter to confirm, and then making sure you're not snapping to the bottom of the model. You can make sure so as not to snap by holding Alt key. That will temporarily disable OSnap, as can be seen down here. You see, holding down Alt and it toggles OSnap as inactive. Okay, so holding Alt and then clicking and then releasing Alt because it's not necessary anymore, we can make a plane here, just a totally flat plane. But as a default, it will be positioned at Z0, and thus it will make it a suitable and representative bottom height. Then we select this solid polysurface, this landscape model, hold Ctrl and Shift and press S to activate the splitting command. And then as a cutting object, we select this plane and we press space or enter to confirm. We hold Ctrl and click the above element here so as to deselect it, and then we can delete everything underneath. We can delete the plane as well here. Now we have a model here which is open. It is because it does not have a bottom, since we split the bottom away. But any geometry with planar openings, that is, openings where a totally flat plane would cover it without any air gaps, can be easily closed with the command cap. So we type cap and space or enter to confirm. This makes it a closed solid polysurface again, and we can see that it is closed. We can toggle the dpFieldmap parent layer on again, and here we have our first landscape model. This first method is very straightforward, generates a smooth approximate of the height curves, but takes a lot of processing time and also some liberties with what happens between the height curves. So for the second method, we're going to use the built-in Rhino plugin Grasshopper to make a terraced landscape model using the actual height curves. We can hide the dpFieldmap layers, but only to hide the patch from curves layer, but it is marked as active, and an active layer cannot be toggled as invisible, so thus we make a new layer called surfaces from curves. We'll mark this as active, and now we can disable the visibility of this. Then we can show the dpFieldmap parent layer again, so as to start anew. We can save as well. In the definition we're going to use for this, we will make use of two additional Grasshopper plugins, Human and Elephant, and the links for these are included in the description. Let us first start Grasshopper, and then we'll go through how to install additional Grasshopper plugins. Start Grasshopper either by clicking this icon, or by typing in Grasshopper as a command. Press space or enter to confirm. Wait for the plugin to load. After loading, it opens a separate window, which can be positioned anyhow you want, and is still kept in front even when the Rhino window is active. To add additional plugins, go to the Food for Rhino website, link in the description. Here, you can search for Human, as well as Elephant, and download the plugins for your Rhino version. Food for Rhino requires an account to download the plugins on its site, and either you create your own personal account, or to lower the temporal threshold, you can temporarily use a publicly shared account found on the Bug Me Not website, link in description. Then, when you are logged in, you can download the plugins for your Rhino version. I will download here for Rhino 6, and I will download here for Rhino 6. Go back to Rhino and Grasshopper, click File in the Grasshopper window, Special Folders and Components folder. This will, in File Explorer or Finder, open the folder where plugins are loaded into Grasshopper. In another File Explorer or Finder window, go to your downloaded files. Any Grasshopper assembly file with the file suffix of .gha can be moved directly to the directory. But if it is a zip archive, then you must first extract it. And then move the GHA file from inside to the components folder. Having moved both plugin files to the correct directory, you must restart Grasshopper to load the files. This is done by exiting Rhino and opening it again, and starting Grasshopper with the command Grasshopper. Now you should have human and elephant tabs in the Grasshopper toolbar. To temporarily recover full sight of Rhino, you can double-click on the Grasshopper window bar. Double-click the Grasshopper window bar again, and move it to the side so that the Rhino layer pane is showing. Now it is time to start defining the Grasshopper definition. I will start here on my end by adding a bifocals node here, which will make sure that all nodes and components here will show both their... I will add a curve here so as to make this more evident. There is a plugin called bifocals, which basically adds the names of the components as well as the icons so as to make it more obvious for you to replicate. Without bifocals, the icons do not have this text. Alright, we'll begin by actually keeping this curve component, because this will be the curve component that references our crop rectangle. So we can either double click the window pane so as to window bar here so as to more clearly see the Rhino viewport. Then we can select this, the rectangle, which will be used for the crop. And then with that selected, we can right click on this component and set one curve. If one curve was selected as it was, it will be now referenced here in Grasshopper. And this can now be more clearly shown if we double click here again and we disable both dpFieldmap and a free layer where the curve is subsiding. Then we can see that Grasshopper references the layer, or not the layer actually, but it references the rectangle in the layer. It references the rectangle. Even though the rectangle is not visible in the viewport, it is still referenced here in Grasshopper. You can make this more obvious by, if you, this is very important and I forgot to say it initially, but if you double click in the canvas, then you can enter a search word and then it's keywords, and then if you type curve, then you see that you have the top dozen results for your search keyword. So curve here, and I want to annotate this, and annotations can be made with the tilde key, and on a Windows Swedish keyboard you hold Alt-GR to the right of the space key, and then you press the circumflex, the key closest to the left from the enter key, and then press space so as to make that tilde character without using it to make a Spanish N or something else. Press enter, and that's a scribble for you. You could also, while pressing Alt-GR and the circumflex and the space, and then you can actually type here, crop rectangle. Then that will be the text produced. So I can delete this, select it with clicking and click and press delete. So this is referencing the crop rectangle. And to make it properly crop all height curves, no matter where the height curve is positioned in the Z axis, then we can make this curve a planar surface. In Grasshopper, planar surfaces are called boundary surfaces. So double-clicking on the canvas, start typing boundary, and then the top 12 results are listed here. Alright, and then with this curve referenced, we can drag from the output of the component. This is like Swedish or English, you read from left to right. and the inputs are from the left and the outputs are to the right. So you click and drag from the output of the curve to the input of the boundary surface. This will produce in Grasshopper, so separately from the Rhino viewport but still showing in the Rhino viewport, a planar surface, a boundary surface, defined by the rectangle that we have referenced. And then to make this a solid entity which extends through all height curves, then we extrude this. Extrude is extrude here as well, so we type extrude, double click, extrude, and then click or just enter. And while this top 12 list is showing, you can, with the arrow keys on the keyboard, you can navigate to which one you want. And click on it and delete. So we will extrude this boundary surface, and this is also important to say here initially. I will move this a little more to the right so as to show more of the viewport here. That as default in a new document, everything is showing. So the reference curve is showing, the boundary surface is showing. If we connect this planar surface to the entity that is being extruded, the base that is being extruded, and if we add a direction, perhaps a Z direction, a vector pointing straightly up, then this will extend or extrude exactly 1 unit upwards in the Z direction. And all of these are now showing at the same time. And initially this might not be a problem, but the more components you add, the more cluttered your Rhino viewport will be. So then it can be good to enable this option here, which I think is called only draw preview geometry for selected objects. And that makes everything hidden by default, but when you click on it, you see what is showing. So that is something to consider. But as of now, we can click on it again so as to toggle it off and showing everything. Right? We want our cropping box not to extrude only 1 meter, because then it would not even reach. I can double click here and show the dpFieldmap layer, and you see here that it does not even extend to the first height curve. The lowest height curve is 9 meters, and if you want to use this rectangle turned into a planar surface, turned into an extrusion of a box, then we want to make sure that this box or this extruded surface extends throughout all of the height curves. So I can, we can keep this on, and I can double click on this, and then here you see that the multiplication factor of the direction that the surface is extruded is right now 1, and since the unit here is in meters, then it is 1 meter. And we know that I think it extends from 9 meters to, was it 45 meters or so? So having it extended or extruded 100 meters will be more than sufficient to contain all of the curves and to trim these within the dimensions of the box. All right, but before we can do so, we will need to be actually referencing the height curves. So we create another node here, or another component called curves, or sorry, curve. One may also, I click on this and delete this, one may also click on an already placed component, click and dragging it, and while clicking and dragging it, clicking once on Alt. That will make it a separate copy, but it will copy also the properties of the already placed component. So this one already has that rectangle referenced. But if we clear the values, now it is clear, and also if one would set multiple curves, then that would overwrite the one curve it had been assigned or referencing. All right, but this component here will need to be referencing all the height curves. So we double click here to show, and then we go down to our created parent here, the height curves layer, and then we can right click, select sublayer objects, and now we see that these are all the height curves. They are selected. We can double click on the window bar here. We can right click on this curve component and set multiple curves. Now all of them, all of the selected curves are referenced here in the curve component here. We can verify this by double clicking on the window bar here, disabling the visibility of dpFieldmap, and now we can see here that we still have a visual remnant of the reference curves. And now if we would want to only see these curves, then we could toggle this and click there. And one can also do like this, that if you toggle that off, if you find this box to be too occluding, then you can, with a component selected, you can click the middle mouse button, the scroll wheel, and then this blind guide you can click to disable preview of that extrusion. Now we need the component trim with brep. So I'll search for trim brep and trim a curve with brep. And we want to trim not only one curve, but all of these curves. And since all of these curves are referenced in this curve component, we can just input this curve, or these curves, but this curve component referencing all the curves, into the curve input of the trim with brep component. And now that we have these curves referenced here, we will need to have this extrusion referenced here. And it was not showing because we picked it to be preview disabled, but we can enable the preview again to see that this is the one we want to use as the brep, as a trimming brep. So we will drag the output of the extrusion to the input of the brep to trim the curves with. And now we can click this, and we see that it has 45 curves that were split, or it was 65 curves, and of these 65 curves there are 45 segments which are inside the brep. Oh, and the brep is the boundary representation. So a mathematically defined geometrical entity, in this case a very simple box. That is the brep. And we had 70 curves, or 70 curve segments outside of the box, outside of the brep. And now we are only interested in what is inside of the box that was used to trim the curves, since that is our intended extent of the landscape model. So we'll double click in the canvas, and we can use a component called flatten tree. And this will also introduce you to the tree structure in Grasshopper here. If I double click again and press hold shift and press 2, which makes it a quotation mark, and press enter, that will create a new panel, and a panel holds text information. And even though the information or the data contained here are curves, the curve data can be converted into text information, giving us information of the curves. And not only of the curves, but also the data structure, the tree that it is contained in. So here we can see here that the tree structure is quite long here. I'll extend it so that it is full here. Oh, I will not do that. I will just scroll a little. And here we can see here that the data structure here, it might seem a little confusing as to why are these empty, why do these have 1 in them, and why do this have 2. But the data structure is always logically created. So in this instance, we got, if you see here, 0, semicolon 0, 0, 1, and continuing. It's always 0, that's the first part of the data structure. And then in the second path, it's from 0 to 64. And this is because the indices always start at 0. So 0 is the first index, and then it continues. So with index number 64, that means that it's the 65th branch in that path. And 65 branches is very logically connected to that it is 65 curves that were input to be trimmed with this box. So each of these branches contains what the trim with brep component did with the original curves. So from the first curve of the referenced polylines, there is no curve that is inside of the brep that was referenced. While in the, let's see here, 0 is 1, so in the first, second, third branch of this path, there is a reference to a curve that is inside the box after the trim. This means that the first and second referenced curves did not have any part of it inside of the box that was trimming it. Instead, if one changes to the outside curves, one can see that the first and second curves have one whole curve each. While the third curve, here in index 2, one can see that on the outside there are 2 curves, and that would imply that the one originally referenced curve has been split into 3 parts. That would make the assumption valid that this has one polyline curve in its third branch. I know this might seem a little confounding, but rest assured, every data structure tree that is created in Grasshopper has a logical genesis. But for this part of the definition, we do not need this data structure, so we can flatten the tree, is called. That is simply to eliminate all the paths and all the branches and to just retaining the order of the referenced objects, the actual curve segments that were inside of the box. They are all stored in one single branch, 0. And here we can see that since we reference only those curve segments that are inside on the trim, then we can also see here in this green U that that is correct. I will select this text panel and press delete to delete it. And the next step is to order all of these interior curves in Z height order, so as to make all coplanar curves, all curves which are positioned in the same plane, at the same Z height, that they are grouped together. But first, let's clean up this preview a little. Like previously stated, one can activate this, but that has the drawback of only showing what is actively previewed. One can also select everything by click and dragging in the canvas, and then clicking the middle mouse button, and then disable the preview, and then show what is most interesting to us. So we will show what we have here, and that is all that we need to have previewed for now. Alright, to calculate the Z height of these curves, we already know that all of these curves are planar. They are moving in the X and Y directions, like this, but they are not moving at all in the Z direction. They are horizontal. Thus, we know that any point on the curve is the same height as any other point on the curve, and thus we can double click here on the canvas, type endpoints, and reference these curves that we have referenced here, the curves that are kept inside of the trimming box. And then we can reference those. And now we find that here we have all the endpoints, and as previously stated, the start points and the end points and all points in between anywhere on the curve is of the same height as any other point on the same curve. So we can take the start point here and a point, as you can see here, or if you double click and shift to a quotation mark and enter and drag from start point to the panel, one can see here that each of these points are constructed in the same way. They got an X value, a Y value, and a Z value. While the x and y values are very large due to the choice of the coordinate system, we can see here that the z height is consistent in being integers, no floating decimal points, and we can order these curves based on their z heights if we deconstruct this XYZ composition. So I'll delete this panel and I'll deconstruct point. And there we have it. Deconstruct a point into its component parts. So I'll deconstruct all of the start points of all of the interior curves here. So you can see here that here we have all the curves. Here we have all the start and end points. And here we have actually nothing shown here because this is referencing a point and the point is shown here in the viewport. But this is deconstructing the point into its mathematical data. So an x value, a y value, and a z value. And we will sort a list. We will sort this list from its z values. And a sort list, it's very simple. It's a very simple component. It takes inputs in numbers, which this has been deconstructed into numbers, and these z numbers are integers and very easy to sort. So we'll input this as the keys to sort. And this will reorder all of these values into an order where it is from lowest to highest, from A to C, from 0 to infinity, or from actually minus infinity to infinity, of course. And the amazing thing about this very straightforward component is that the sorting it does on the keys of the values referenced in the input here, the same sorting can be done for any type of objects which has the same data structure. And since this component has 45 curves, this of course has 45 starting points because each curve has one starting point, and each starting point has one z value, then this sortable value has the same data structure as this value consisting of curves. So we can input these curves into the sort list here, and then we get out here, and this is not very evident, but since it looks the same way. But these are the curves sorted from lowest z height to highest z height, and these are the curves in the original order. This can be more clearly shown by using a list item component. By default, if you drag any data tree into the list item, it will reference the item index 0, so the first one in the list, and then you can click and you see that this is this. So this is, according to the sorting, this is the lowest curve. Of course, it's the same. It has the same z height as the one here accompanying it here. So both are 9 meters above sea level or 9 meters above the z0. But if one duplicates this by clicking, dragging, and while dragging, clicking once on Alt, then you will creating a separate copy. And a copy is always by default attached to the same components that its parent was or that its original was. But this can be easily one can either hold control and drag the same connection, that will remove the connection, or one can also simply overwrite by dragging from another connection. So here we see that in this unordered list of curves, this is the curve with the first index, the first referenced curve. But in the sorted, it is this, which is more correct. If you zoom in, you can see, you can click here on the plus sign. It will mean that it will reference the first index of the list, of the reference list, but if you press plus here, it will also reference the index 0 plus 1. And now you see that it's these two. If you press once more, it's that. There. So now you see it goes in order. And I see that I was incorrect in thinking that this was the same height as this, but obviously this was the same height as this. It might be more appropriately shown if you go to the front or right viewport here. Let's see here. Yeah, here you see that those two have the same height, but that one, the 1, 2, 3, 4, the fourth reference curve has a different height. While the same one here, that's the first one, second one, third one, fourth one. It's not even ordered anyway. Okay, I'll delete this and I'll delete this. And I'll go back to the perspective viewport here. All right, the endpoints we can, if you click and drag to select, and then you can click middle mouse button and disable the preview of these. You don't have to see them. And here we have the sorted curves according to the said height here. And now, since we previously said that we want to group curves which have the same said height, because right now we can, since we know that the curves are sorted in the same way as their said height value, we can show here in a text pane the actual sorted values, not the sorted curves, but sorted values. And we can see here that we have a data structure of only one branch, and the one branch has all the curves said heights, but as you can see we have 3 with height 9, and 1 with 10, and 4 with height 11, height of said 11, and that makes and that means that these 3 and these 4 should be grouped. They should be in a data structure where they share the same branch, so that they as a group can trim the surfaces that we are going to create for each said height later. Alright, I'll delete this. And then we can use a component called createSet. And createSet does precisely what we want, because it takes an input. I can actually still show this so that this is evident. It takes an input and creates, like you saw here, like you perhaps saw it, it creates a new set with individually unique entries. It does not change the data structure, so it's still one single branch, but it's not with 3 of the same value, 9 here, but instead is only 1 of the same value. But this in itself does not help us. We will need to be using a component called assign paths. And this assign paths component, it's a part of TreeFrog, which is included in the human plugin, and that is why we installed it. So I will type in here, after double-clicking the canvas, assign paths. And this will need a data input and a paths input. And the paths we have created with this createSet, and the data, and we have here with these sorted curves according to said height. So the data is given, it's these curves, these sorted curves, and then this createSet component, it has 2 outputs. One, it has the set as list, and that is what we have referenced here. It shows all the individually unique items in the new set that was created. But it's also got a map, and that map shows, if I replace the input here for the text pane, it shows to which index each of these values was referencing. So you see here that the index 0, 9 is referenced 3 times by the 3 first indices of this layer, 999. In that way, we can use this map to create new paths so as to make groups of these curves, one group for each said height. So I'll use that as paths. And then if we create another, double click on the canvas, hold shift, 2, quotation mark, panel, and enter, then we can see here that now these curves have not only been sorted here, but also been appropriately grouped in separate branches, one branch per said height. With this accomplished, we can use all these individual branches, some consisting of 3 or 4 curves and others of only 1, as individual trimming inputs for the surfaces that we are going to create at each said height. This is great. Speaking of these surfaces, I think that it's time that we create them as well. So we'll go back to the crop rectangle. We can show the original, we can show the preview here of the boundary surfaces that of the boundary surface that was created from the referenced crop rectangle. And so as to make sure that no matter where we placed this rectangle, now it was placed in Z0, but in Z0 there are no height curves, because they start at Z9. So to make sure that we create a copy of this boundary surface, but that each copy is placed only where there are actual height curves, we do like this. We calculate the area of this surface, double-clicking the canvas, typing in area, clicking area, or just pressing enter. Not because we are interested in the area, but because by calculating the area we also get the centroid. And the centroid is, like it says here, the area centroid of the geometry. The centroid is a single point straight in the middle of the reference geometry. So we use this centroid, but then again, like with the deconstruction of the Z value of all the height curves, we are only interested in the Z value here. We don't want to move it to the side, to the X or to the Y. We only want to move it up to the respective height, to the respective height curves heights. So we can deconstruct this point as well, this centroid point. Let's see here, I will make a little space here. If you feel that things are getting too cramped, you can hold down Alt before clicking, and you see here tap Alt to toggle separate direction, and then you can tap Alt again, and then you can, by still holding the left mouse button, you can drag a little there, perhaps drag a little, I don't know why one would drag precisely there, but I just want to demonstrate that it goes both ways. And as one can see here, we got an X value, which is this, the X value of this, and a Y value, which is the same Y value for this. And the Z value is not important, but it's 0 because it's positioned at Z0 height. But we'll construct a new point, or actually a new set of points. Construct points there, consisting of the same X value and the same Y value, but it should have, you can position this here as well, it should have as Z value only the values here. So these 35 unique Z heights. So we click and drag from there to there, and now you see here, it's very important to notice that these single lines mean that only a single value is referenced. So you see here, it's a single value, and the same here, single value. But when there's 2 lines like this, it means that there is several multiple values, but still one branch. So if you see here, it's 35 values, but all are in one branch, like you see here. The data structure is one path, one branch, and everything is in one list. But then again, this third type is if you see the dashed line. That means there are objects ordered in a data structure with several branches. So here we have only one path. You see that we have 0. Where did we have an example with several paths? I think here. Yes. Here you see that we have 2 paths. The rightmost path, there are several branches. In the leftmost path, there is actually only one branch. And that is because there is only one brep that we trimmed these 65 curves with. But nevertheless, if it has multiple branches or multiple paths or both of them, it's still the same. It's a dashed line. But as you see here, a dashed line with several branches with multiple paths gets flattened into one data tree with 45 curves in one branch. All right, that was a long parenthesis. Here we have constructed then a series of points. They all share the same x and y values. They share this particular x and y value, but they all have z values corresponding with the 35 unique heights that these height curves have. So in theory, and if we might assume that practice follows theory, in practice we have one per each height layer that the height curves are representing. Okay, I'll delete these panels. And then we need to move the original boundary surface. So we can use the move to point there. And what we need to move is this boundary surface. See here, and to make this a little more aesthetically pleasing, we can do like this. Something about it. Okay, and we move from point, that should be the original centroid. Yes, this, from that to all of these. That would in essence make copies, because you see that we have one geometry, the untrimmed surface, and we have one original point, but we have several, or 35, endpoints, or points to move to. And that actually in practice makes it as the same as copying it to these 35 places. So if I click this, you see that we have 35 referenced planes here, or planar surfaces made from the rectangle. All right, it's time to hide some. Let's see if we can hide. We can hide the original surface so that we have only the copied visible here. But it's still a little cluttered. We'll fix that in a minute. All right, and then we will need to split all of these curves. You see them referenced here. If we temporarily disable this, you see that these are the curves. We can actually disable the preview of that as well as this. So, and then we have all of these, one per each layer height. And then we will need to be using a component called surface split. It does precisely like it says, surface split. It splits a surface by a bunch of curves. But before we do that, we will need to make sure that the data structure is perfectly compatible, because here we have a list of surfaces in one branch. You see here that it's only 2 lines, no dash. And let's see here. Here we have a data structure with one path with several branches. It should be 35 branches, yes. And that is not by default compatible with what we intend, because we want each of these surfaces to be trimmed by only the curves of that particular layer. But it should be no difficult matter to make those compatible, because like we said, we already have all the surfaces here, and they are 35, and each one of those individually should be trimmed by the set of curves, the branch of that certain height. So it should be only to graft a tree means that you create a new path, a new branch for every individual object in a list. So if I drag from this moved object to this input data tree, and if I add another text panel, we can see here that here we had 35 surfaces in one branch, and here we have 35 branches, and in each branch there is one surface, and that is what we want. One thing that the graphed tree did here is that it made a different data structure than what we have here, because here we have only one path with 35 branches. Here we have two paths. Path A and path B, I think is the correct way to reference them. But in this right-hand path, we have several branches. In the first one, or in path A, we only have one branch, 0, 0, 0, 0, 0, 0, 0. But we will need to remove that common branch so that this has a compatible data structure with this. So I will type in here simplify tree, and as you see here, it will it's very pedagogically describes what it does. It removes all paths which are shared among all items. So if I insert that here, and we can see that it's changed this so that it has the same data structure as this. So 35. And I say 35 because all indices start at 0, so 34 automatically means there's 35 indices. All right. And then we can actually, because these are the surfaces, so I'll drag that into the surface there, and these are the curves, and I'll drag these into the surface split there. And this took 2.7 seconds here. It might take longer or shorter depending on the complexity of the curves. And then one could actually, because this is the result that we want, but it is not in any way ordered. If I would right click on this output and bake this, one could bake it into the surfaces from curves layer and check this, yes please, group these. One could press OK, and it is baked, and I can click here, and we can just for viewing it, we can move it out here, and you see here that we have all the surfaces not trimmed, but split by all the curves, and then we only need to remove the excesses. We only need to remove those parts which are not part of the landscape model, but which are those areas which have been trimmed away, or which we manually trim away. But so one could actually be satisfied there, but I think that we should strive to make it a little more orderly. So I will delete this group that we exported, that we baked, and then return here. And then I will introduce Elephant. And Elephant is a plugin that does many things, but in terms of baking, it's one of the most competent. So I can type in here bake objects, and you see here the bake objects there. That's the Elephant one. If you hold down Control and Alt and click and hold, you can see where a component is subsiding, in which tab and in which toolbox. All right, and we need another elephant component here, which is called get attributes, I think. No, not get attributes, but define object attributes there. And we drag that to the attributes here. And these are the surfaces that we want. And to actually make use of this functionality to make things more orderly in proper layers, we need to add this layer information. And this layer information is made from the set we have created here. Because these are the said heights of each individual branch that we export. 35 branches, each with different amounts of surfaces. But each branch is situated on one individual said height, and this is the same said height because we chose this there, referenced there. So, but then we need to make this data structure match this data structure. So here we can create a new panel, check out what we have, what the data structure is here. So we have two paths, and we have we actually have in the first path, in path A, we have 35 branches. As then in the second path, in path B, we have, all are in branch 0. But a good thing about the simplify tree component is that it works both ways. It can both make sure that common paths here is eliminated as well as common paths here. So now when we input here, we can see that is correct. Yes, we got 35 branches in one path. Very good. All right, I can put it there so to make sure that it's not. All right, so now we have 0 to 34, and here we should have 0 to 34 as well. So I guess that we should graft it. We should graft the tree. By grafting it, we have 0 to 34, but we have multiple paths, and the path is common, so a simplified tree will be doing that very elegantly. So here we have an input, and the output is perfect. Yes, and these very common data structure manipulations, they can actually be made both on the output and the input of any components. You can right click here and you can reverse, is reversing the order of the list. Flatten we did here with a separate component. It makes all the items of any data structure into one list of only one branch. And graft makes one new branch for every individual item, and simplify makes sure that branches that are shared among all items are eliminated from the data structure. Let's see here. There's a simplified tree, and now that should be 0 to 34, and here we have 0 to 34. And like you see here, we can test out with the first index here, with index 0. This means that all in index 0 are matched against index 0. So these 4 trimmed surfaces will be matched against the number 9 here, and we will make sure that the number 9 is part of a layer name that we'll be using for the exportation, for the export, while index 13 here is going to be matched against the number 22. And maintaining a data structure is very good, so as to make sure that you can do many things at the same time while not having to matching like 64 objects against 64, and thus forcing very computationally intensive computations. This is no hard matter at all for the computer to make, but it's it's more strenuous, or it's more demanding to keep these data structures in check for you as a user. Then we can create a new, or we don't need to create a new panel here. We can just reduce the size of this one, delete this one, delete this one. And here we have all the values here, but since it's showing in a panel, it's interpreted as a text element. And then we can add another text element. And when you double click in the canvas and hold Shift and 2 to make a quotation mark on a panel, as with the annotation, the note that we made here in the beginning, that we forgot to make here. These are all the, let's see here. Yeah, these are all the height curves. So I can double click there, Alt GR, circumflex, space, and here you can type immediately height curves. The same way here with the panel, you can double click, Shift 2, quotation mark, and you can start typing immediately. So now is the layer name, and I think a fitting name would be height curves. And then when it comes to layers in Rhino, double colon, and colon, that signifies a sublayer. So if you define here that the layer name should be height curves, colon, and then everything, all individual branches of these, that means that we create 35 branches, the first one being height curves 9, height curves sublayer 9, second height curves sublayer 10, and that is precisely what we want. Press enter, and then when you want to combine text in Grasshopper, it's called concatenate. So you double click, type concatenate there with the ampersand, and then A to B, and here we can see in the panel how it looks like this. And like I said, all the double colons are going to produce a sublayer with what follows being the sublayer. So it looks like we want. Put that into the layer name there, and now we are actually ready to bake. So now I click bake here, activate, and everything has been baked here. When you click bake here, it can flicker very much here in the layer pane when Grasshopper commands Rhino to create these new layers. But now you see that we have height curves parent layer with all the individual heights as sublayers. Very nifty. And now we can double click here. We can click on that and have nothing selected. Then nothing will be showing in the preview. And then we can double click there. All right. So if one would show the dpFieldmap layer again, you can see that we have the dpFieldmap layer, and we have the top. You see here the top surface. But as you also see, we also have all of the excess. I can delete this right now, and you see how the next layer is showing, and we can do that and do that. But it's quite a manual work to do, so we can by holding control and pressing Z and Z and Z, we undo those, and then we can hide dpFieldmap again. And then here with the height curves layer, I can just make sure so as to not remove the... Oh yeah, actually we have already disabled the visibility of this. I wanted to make sure that we don't remove it, that we don't by mistake delete it. But then here, if you look at the logic with the landscape model and the logic with height models, height fields, and all of these representations of landscape, is that they are produced most often by laser from an aeroplane. And that means that it captures very accurately the topographical flow, but they cannot capture cavities like caves or subterranean structures or such. It only captures the top layer of the Earth. And knowing that technological limitation, we can assume that nothing, if we look at here from on this landscape model from below, and we see here that here it's very evident what is the actual landscape and what is not, what is void and what should be removed. So if we identify this, then we know that everything above this should also be removed, because in a landscape model, nothing can exist above void, because the technology that captures the landscape has that limitation. So having identified such an area as this, we can go to top viewport, and that is already selected there. And then we can hold Alt so as to make sure not to drag it, and drag from the right to the left. If you drag from the left to the right, it will only select what is completely within the rectangle. If you drag from the right to the left, then it will capture or select everything that is at least partially contained within the rectangle. And since we knew, or since we identified here in perspective view, that this one should be removed because it is void, then we know that on top of void cannot be mass. So everything above that void must be void as well. So we can, with this selected, we can just press delete, and already there we have much of the work already done. And then of course you have to check here, and if you see here that there is mass, and then this is evidently mass, and then there is a separate entity, then that should be void as well. And above that void there was nothing. Let's see here. I think this is in the same. I did now was I selected it. I typed in ZS zoom select, and that will orbit it around the selected object. And this was obviously void as well, so I'll delete that. And let's see here. If you hold Alt and drag, you make sure that you don't accidentally drag. If you drag here, you can accidentally drag that object, which you don't want. Control Z to undo. All right, zoom select. Looks okay. It's a little small, but it's okay. Yeah, all right. I think that we got it here. And now you see also here that this is the level 9 height layer, but underneath there should be a level 8. Of course, the height curve signifies at what height that height actually is, and thus where there's no height curves represented, there will be no plane automatically created. But as long as the lowermost layer, this layer 9, layer Z height is 9, as long as it extends throughout the rectangle, then you can just, with it selected, type bounding box. For a more three-dimensional object, this will create an actual box. But since this is only a plane, it will create, even though the output is assigned as a solid or defined as solid, it will create a curve. With that curve created, you can type in select last, cell last. It will select the last generated object or the last selected object. You can type in planar surface with SRF as an abbreviation. To make that curve into a planar surface, you can delete the curve by pressing delete and cell last again to select that again, to select that generated surface. You can press M for move, either typing fully move or just M, picking actually any point, but not before you have either clicked here on vertical or typed in V and space or enter to confirm, so as to make sure that movement is only vertical. Then clicking on a point, and with the vertical movement initiated, you can type in -1, as in -1 meter. So that would be 8 meters. And then you can click on that newly created surface. You can click here on height curves, sublayer 9, click on new layer, type in 8, press enter, move that up 1 step, and right click and change object layer. This will change the selected object into the layer 8 here. And there we have to say that it is complete is a little premature because right now, as you see, it's only planes, it's only flat surfaces, but it's a fairly accurate representation of the height curves exported from dpFieldmap. But to make it an actual 3D model, one would have to select all, either by dragging a window completely from the left to the right here, or by right-clicking and select sublayer objects. Here we can type in the command extrude surface, extrude SRF. And this will take, I will just warn you that this will take a long time. But just check that it's creating a solid, that it deletes the input, these individual surfaces. And then the direction is by default the direction of the normal direction of the surface. That is the perpendicular direction of the surface extends. If it's extending like this horizontally in X and Y axes, then the normal direction is perpendicularly the Z axis. So by typing in here, each of these surfaces are 1 meter apart from each other. So logically, we would like to extrude this 1 meter and make sure to extrude 1 meter down so as not to skew the model 1 meter too high. So -1 and enter, and this will take a long time. Saving before is also very recommended. Now we're back, and all of these individual surfaces have been extruded exactly 1 meter down towards Z-, and it looks good. This is a terraced model generated from the height curves exported from dpFieldmap. And let's see here, and it was created in the active layer, surfaces from curves. And as such, we can, I think that this, since it deleted the input, I think that this is an empty layer. Yep, there is no objects in the height curves, but if one would like to export those curves again, they are easily baked by clicking activate on the Grasshopper window, which I cannot find now. There. By pressing activate again, I'll just collapse this and hide it. And then we can set the 0 layer, the empty 0 layer, as active, so as to be able to freely check here, freely toggle the visibility. So let's see here. Here we have the patch from curves. And here we have the surfaces from curves. To make them more looking alike, one can take this lowermost plane, and I think the most straightforward would be to extrude SRF, and then you can select the lowermost surface of that polysurface, and then extruding it down. Let's see here, we got this on top of here, it's 9 meters, on top of that is 8 meters, so below this would be 7 meters. So pressing enter to confirm the selection, and then -7. Oh, and then it was, of course, because it's the normal direction, and it was the surface was facing down, so -7. Oh, but we can just point it there, and then it's gonna be good, like that. So now they are more alike in terms of size, but I think that it was one distance, 7 meters, 8 meters. Let's see here. From there it's 9 meters, but is this at 0, 1, or is it? Yeah, we can confirm this here, that if one has the surfaces visible and shows the dpFieldmap, we can see that I think that the extrusion, like I by mistake assumed that by typing -1, this lowermost bottom surface would extrude to the bottom, but since it was by default in the normal direction, then it extruded up unless we move the cursor up, and then it's actually turned down. I think that I, by mistake, extruded this up once more. Everything, looking at the dpFieldmap original curves, everything speaks for that. So what we do then is simply to right mouse button click the surface from curves layer, select sublayer objects, move with M, V to constrain the movement vertically, press any point here, and then -1, and then click to confirm, or space to confirm. And now we see here that the top of that layer is aligned to the original curve, and that is what is intended. And then hiding the dpFieldmap parents, one would assume that these are more aligned. Than, yes, one can see that here as well. All right, and here one can see how the patched surface might look more smooth, and that is a quality in many endeavors. But the surfaces from curves is more accurate in terms of the input data, because there are no interpolations made here. This area here is not interpolated to be bulging upwards or downwards, while here one can see that it moves more bulgy, that it moves more than one would assume. One could also see that quite clearly here on the top, because the height data defines this as the top of Osotoilun and of this area. But the interpolated path, it thinks that this should be the top. And that is of course affected by the settings used when making that patch. But as a bonus, we just want to show that you can now, with these surfaces from curves and these surfaces extruded and correctly placed, one can also do like this. I will change to top view here, and having in perspective view already made sure that this surface from curves is what's showing and only showing. We can in top view, and if the layer hierarchy should be honored, which it should, then we should make a new layer here, should called Drape from, let's see here, Drape from surfaces, and make that active. And then there is a command called Drape. So I will type in Drape here. And then the spacing here is the same spacing as the UV span spacing in the patch command. Yeah, actually, this it's an inverse relationship here, because here the lower the spacing, the more dense the surface defining curves become, and here the higher the value, the more lenient it becomes on the original geometry. So 25 here we can test, and Drape command works like this. It drapes anything that is projected underneath in the view. So in the top view here, and with the Drape command active, and if you would start the draping process outside of any geometry, it will extend below. It can of course be manually trimmed away after, but generally it is recommended to keep inside the geometry you want. I started now here in the higher left corner, and I'll go down to the lower right corner, releasing the mouse button softly. And as you see, it created a surface, or perhaps, yeah, it's created a surface. So we'll go to the perspective here to show. We can type in select last, cell last, and we see that it created a surface. I can create a copy of it by holding Alt and dragging the gizmo here. And we see that this surface here, it has the advantage, like the patch has, that it is, let's see, it's, I will temporarily hide this drape that we did. Control H to hide. This drape has the advantage over the patch that there are no actual interpolations made, or like if it's a flat area, then it is as flat as it was in the height curves. While here in the patch, it makes these interpolations, which are also shown here as well. So I guess that's actually in the that's actually in the height curves data, but this bulge here is definitely not on the top. And since this was made from the terraced landscape model that we did in Grasshopper, it does not have that height over the height of the highest height curve. So that might be advantageous. And this was with a spacing of 25. If one changes the viewport mode to Arctic, perhaps, one can see that they are quite similar. All right, shaded, and this can as well be done like we did with this. We can extrude this surface down, we can create a plane, we can create it, and we can split this with the plane. We can control click that, and we can delete that and delete that and select it and cap that. And then we have that there as well. All right, and with the surfaces from curves showing as well, we can actually do like this, select sublayer objects, and I can make a copy of that there. Control, right mouse button click, select sublayer objects, control and drag so as to deselect that and hide that, because now we have all these free models here. So here we have one made with a patch command from the imported height curves. Here we have a terraced model made with a more strictly adhering to the height curves, and here we have some sort of intermediary model or method using the terraced model as an outset, and then draping that with a more smooth surface over. And I think that should conclude this tutorial, which has drifted a lot, but I hope that those who wanted to learn something has done so, and have skipped those parts that were not interesting, and have indulged themselves in those parts that were most interesting. All right. yeah, thank you very much.